Okay, looking at question 5, we'll be discussing reaction mechanism. Okay, so for reaction mechanism 5a, we are supposed to deduce if each of the following reactions is elementary or non-elementary reactions. Alright, so there are two new terms over here, elementary, non-elementary. So recall, elementary reactions are reactions that happens in a single step. Alright, and typically the rate equation or the rate law will be based on the stoichiometric equation. Okay, non-elementary step, more than one step, typically 2 for syllabus, and your rate law is based on the slow step. Okay, so in this case, how do we know it's non-elementary? Non-elementary typically, right, your rate law is it's not based on stoichiometric equation. Okay, so some of you may ask, what do you mean by not based on stoichiometric equation and what is based on stoichiometric equation? So let's take a look at 5a. I'll use the first example to run through with you guys. So in this case, this is the overall reaction. This is the stoichiometric equation, right? So you can see in this case, 1NO react with 1O3. Okay, the rate equation is given as KNO1 O31. Alright, so in this case, you can see that the order of reaction in the rate equation matches the stoichiometric coefficient. So in this case, we can say that the rate equation is based on the stoichiometric equation, and therefore this reaction is going to be elementary. Okay, again, so the reasoning is the rate equation is based on the stoichiometric equation. Again, relating the order of reaction to the stoichiometric coefficient of the overall equation. So the reaction is elementary. Okay. On the other hand, you can see in the second example, rate equals to KNO squared. Alright. Which, when you look at the overall equation, is 1 CO with 1 NO2. This indicates that it's not based on the overall stoichiometric equation, and therefore reaction is non-elementary. Okay, so it's important for you guys to identify whether it's elementary or non-elementary, because if it's an elementary reaction, the stoichiometric equation is the rate reaction mechanism. If it's a non-elementary reaction, then in this case, you need to work based on the rate equation. Okay, so this basically triggers your prior knowledge of what's elementary versus non-elementary. Okay, with that, let's take a look at B, where we are given a series of mechanisms, rate equation, to see which of the proposed mechanism is in agreement with the given rate law. Okay, so for this reaction, 2ICl with H2 to form 2HCl plus I2, the rate equation is given, so this is a useful information. Okay, so likely this is non-elementary, alright, because the rate equation is not based on the overall stoichiometric equation. And since the rate equation is given as this, alright, it must mean that there's one ICl and one H2 in the slow step. Alright, so again, recall your rate equation is based on the slow step. So if you look at mechanism 1, 2 ICLs are involved in the slow step. So therefore, the rate law for mechanism 1 will be rate equals to KICL square. Okay, so 2 ICL square. For mechanism 2, the slow step involve 1 ICL and 1 H2. Alright, and therefore, rate equals to KICL H2. Again, 1, 1, 1, 1. Okay? So in this case, mechanism 2, it's a plausible mechanism because it follows what is stipulated. Alright, so mechanism 2 is a plausible mechanism because the rate equation in the proposed slow step agrees with the given rate law. Okay, so keyword, rate equation in the proposed slow step agrees with the given rate law. Okay, so this is how you show you're working. Okay, if not, we move on to part 2. Okay, for part 2, this is the equation given. So again, this is the rate law. Rate equals to Ka squared B. Okay, some of you may think that this is elementary, but again, given the context of the question, it's not going to be elementary. There are two mechanisms proposed for it. Okay, so focus on the slow step. Okay, let's take a look at for mechanism 1. Okay, mechanism 1, A2 and B. So as a result, rate equals to K A2 B. Right, this is what you guys will write first as the very first cut when you look at the slow step. 1A2, we write 1B in the slow step, and therefore rate equals to KA21 B1. But A2 itself is an intermediate because A2 does not appear as the reactants. Alright, so it's an intermediate, and intermediates cannot be reflected in the rate equation. Okay, so how is A2 formed? A2 is formed from the first step where it involves 2A, and therefore from this we can say that concentration of A2, sorry, let me rewrite that. A2 is proportional to A squared. Alright, so 2A forms 1A2, and therefore I can come up with this relationship. And therefore, if I substitute this into A2, I get rate equals to Ka squared B. Okay, so again, recall, or importantly to note, intermediates cannot be reflected in the rate equation. So we need to convert the intermediate here into an expression of a reactant. Okay, so let's take a look at mechanism 2 then. Mechanism 2, we have 1A with 1B in a slow step. So this is quite clear cut, mechanism 2. So in this case, which mechanism agrees with the rate law? It will be your mechanism 1. Alright, so mechanism 1 agrees with the proposed, or agrees with the given rate law. So mechanism 1 is the plausible mechanism. Okay, if not, we take a look at part 3. Okay, in part 3, we have a reaction of NO with H2. So let's take a look at, again, the slow step, focusing on the slow step. So mechanism 1, we have 2 NO and 1 H2. Okay, so quite clear cut. Mechanism 1, rate equals to KNO square H2. For mechanism 2, alright, what are the reactants? N2O2 and H2. Now, so rate equals to K N2O2 H2. Alright, we know that N2O2 is an intermediate, again because N2O2 does not appear in the reactants. So importantly, right, we need to find how N2O2 is formed. Now N2O2 is formed from a preceding fast step from 2NO. So which means I can write N2O2 is proportional to NO square. And therefore I can substitute this expression into this, and I get my rate equation to be K NO squared H2 for mechanism 2. Now in this case, both mechanisms are plausible mechanisms because both agrees with the rate law. Take a look. Alright, so mechanism 1 you have this rate equation, mechanism 2 you get this rate equation, and both agrees with what is given. But which is a better mechanism? Mechanism 2, it's a better mechanism. Why? And this is a new concept that is not really developed in your lecture notes. Why is mechanism 2 a better mechanism? Because the proposed mechanism does not involve 3 particles in a single step. So you take a look at this. What does this mean? If you look at mechanism 2, 2 particles are involved in step 1. Mechanism 2, 2 particles are involved in step 2. 2 particles are involved in step 3. Whereas in mechanism 1, in the very first step, you involve 3 reactant particles, 2 NO and 1 H2. Now, why do we not propose a mechanism with a step that involves 3 reactant particles? Okay, so this 3 reactant particles in a single step. Why do we not propose such a mechanism? Because it is extremely difficult for 3 reactant particles to have an effective collision, right? Because why? You need to collide with the correct orientation. You also need to collide with sufficient energy in a single step. So it's highly unlikely for 3 reactant particles to collide with the correct orientation and with more than EA in a single step. So this is a concept of effective collision. So highly unlikely, alright? So therefore, typically, the learning point from this question is that when we propose a mechanism, we try to propose a step involving only two reactant particles. Okay, so involving only two reactant particles. Okay, so as you can see in this, two reactant particles, two reactant particles, two reactant particles. Okay, we do not propose a step which involves three reactant particles or more. Okay, that's your part 3. So this is the part that's new. Okay, so you can pause the video now to take note of this learning point, and you can annotate in your lecture notes if you want to. Okay, moving on to C. Now in C, you are given the rate equation, you are given some data here, and you're supposed to propose the mechanism. So in 5A, it's a simple trigger question to test on your elementary, non-elementary concept. In part B, we basically verify which mechanism is the more plausible one. And in part C is the higher order, where we're supposed to propose a mechanism. Okay, so follow me closely. Alright, so we have rate equals to KNOF2. Okay, so from the rate equation, okay, first thing first, focus on the slow step. Since one NO particle and one F2 particle is involved, so take note, one NO and one F2 as the slow step reactants. Okay, NO and F2. So in this case, then what do you form? Now, what do you form? You need to look at the products. So I have two O and F. So I propose, let's form O and F first. So after I form O and F, alright, so I take reference from here, I need to form a product. Alright, from here. So what particles do I have left? I have a F that's not balanced, a F atom. Alright, the dot here basically just shows that this is a radical. Alright, basically no difference from your F atom. F atom has 7 valence electron. So you have an unpaired electron, and that's why we call it a radical. This is what we learn in chem bonding. Okay, so this is also known as your intermediate. Okay, so once the radical is formed, the intermediate is formed, copy down in the second step, because intermediate must be used up. Okay, then now what's then to propose the first step? What's then the reactant? Again, take reference. You need NO and F2. You already taken out one NO, one F2. You have one more NO to account for, and that's why I add a NO in the second step. Okay, and then you can then propose forming your another product. So essentially, when you propose a mechanism, when you sum up all the equations in the mechanism, it should give you the overall equation. So let's take a look. We have 2NO plus F2. The F and F dot is cancelled, and then we get 2O and F, which agrees with the overall equation. Okay, so far? Okay, so this is how you check your mechanism that you propose is correct. So step 1, check sum of all your steps gives you your overall equation. That's first criteria. So first criteria, sum of all steps equals to your stoichiometric equation. And number 2, your slow step agrees with your rate equation. Alright? Okay. Okay, if not, we move on to part 2, justify your answer in terms of relative reactivity of the species involved. Now, so reason why step 1 is slow. So step 1 is slow, meaning that step 1 must have a high EA. So why is it a high EA? Because the first step involves the breaking of the FF covalent bond. So you need more energy. So you expect this reaction to be endothermic, and therefore require a lot of energy, and therefore a higher EA. Okay, and also you form a highly reactive F radical. The F radical is very reactive, so it's less stable. Less stable typically will indicate it has a high energy, and therefore indicate it has a large EA. So if you guys recall, you have an unstable intermediate, energy is high, so you can see the EA will be larger. So unstable, more unstable means higher in energy. Alright, so if you remember your energy profile diagram. Alright, so if I have an even higher energy level for my intermediate, you can imagine the EA to be even higher. Okay, So why step 2 is fast? Step 2 is fast because you have two highly reactive radicals, okay, NO and F, to combine to form a stable product. Okay, so this part, two highly reactive radical of NO and F, this requires some concept of a chem bonding. So let's take a look at NO. NO dot and cross, let's take a look. NO dot and cross. Okay, double bond between the N and O. And you can see that N has an unpaired electron. Okay, N is again electron deficient, 7 electrons only. And then of course you have your F radical. So this electron here and this electron here can therefore form a single bond. So as a result, you form your NOF or ONF. Okay, ONF. Okay, so we form a stable NOF product. Each atom has your octet 8, 8, 8, 10 configuration. Okay, so that's the end of question 5.